Hello students, welcome to Educate. Today we are going to start 5th chapter of class 12 physics. The chapter is named as Magnetism and Matter. So you all are aware about the magnetism, basic properties of a magnet also you know very well. So here some basic points are given, so we can read them together. Like here, monopoles do not exist. Of course, in case of magnet, if you go on cutting it into several pieces, you will observe that every time you cut it, you will get a new magnet with north and south pole. Like suppose this is north pole, this is south pole, you cut it from here. So you will get one magnet here and another magnet here. The same thing, this will become N and S. If you cut further, you will get again another tiny magnet. Although strength will decrease every time, even if you cut it like this. So you will get two magnets. So one magnet will be like this. Suppose here this is N pole, this is S pole. So NS and this is will also be NS. So however small you cut it, every time you will get a complete magnet. It means there will be both poles, north pole and south pole. So that is why we say that monopole in case of magnet does not exist. Here in this picture, here field line patterns are shown. You can see that field lines are like this. If you take this as, suppose, if you take here north pole and here south pole, so you will see that these lines are coming like this. So if this is a magnet, you can just imagine in that case. So field lines will come like this, right? This type thing. You will observe inside the magnet, they will travel from south to north. So we can say that field lines, magnetic field lines form closed loop, right? Here, actually, there is a bar magnet and then we put a paper on it and then we spread the iron filings and we just shake it, then this type of pattern is observed. These patterns show the direction of field lines, right? Now, if we study the properties of a magnet and its field lines, so we will find that the magnetic field lines of a magnet or a solenoid. Solenoid, you know very well what we have done. Suppose this is a coil and then we connect it through a battery and a key. Then it will behave like a magnet. So that is why here it is given the magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike the electric dipole. Electric dipoles, here this is positive ion, this is negative ion. So these lines will travel like this. They can be like this, but they will not come back from minus to positive. This is not possible, right? But in case of magnet, they form a closed loops, correct? Then comes next point. Next point says the tangent to the field lines at a given point represents the direction of the net magnetic field B at that point. Do you understand this concept? It means suppose this is north pole, this is south pole, and you draw field line like this, right? So at this point, if you want to find out the magnetic field, then draw a tangent. So at this point, direction of magnetic field will be like this. At this point, if you draw the tangent, direction will be like this, right? The same thing is given here. The tangent to the field line at a given point represents the direction of the net magnetic field B at that point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field. So, strength of magnetic field depends on number of field lines. So, we can see the figure here where the lines are dense, like here, what you observe. More field lines are there, here field lines are less, here also. So, field strength will be larger in this way. And if they are rarely spaced, in that case we say that field lines are representing weaker magnetic field. Then comes next point, the magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. Do you understand this point? I think you have remembered it at lower level. Like this is north, this is south, and this is magnet, and suppose one line is like this, right? And another line we imagine, although that is not true, but we are imagining that another line is going like this, and at this point they are intersecting, right? So let's find out whether magnetic direction of magnetic field at this point is unique or not. So for this line, direction of tangent will be like this. For this line, direction of tangent will be like this, right? So at this point, suppose this point is P. So at this point, due to this magnet, there are two directions of magnetic field. One is this, another is this. How it is possible? Same magnet is giving two directions of magnetic field at one point. So that is not possible. It means these lines never intersect each other. So this logic. Now here some diagrams are shown. The first one, the field lines of a bar magnet. This is bar magnet, north pole, south pole. Field lines are coming out from north pole and they are entering the south pole. They are forming closed loop. Here some closed loops are shown. Here what is happening? This is current carrying solenoid. Same pattern you can observe. It means a current carrying solenoid also behaves like a bar magnet, right? What about the third one? In case of third one, there is electric dipole, right? So if you remember, in case of dipole, what happens? If this is positive, this is negative. Is it correct? Electric dipole at larger field lines are very similar. Here only similarity is being shown. You understand, in case of positive charge, electric field lines will come out, and at the point of negative charge, field lines will enter. So that thing is shown here. So I think you have understood. There is similarity, but there is also dissimilarity. What is point of dissimilarity here? Point of dissimilarity is here. These lines are not forming a closed curve. This line is coming like this line is coming like this. But in case of a magnet, lines are forming closed curve like this. If you take any line, it will form a closed curve, right? Now, we are going to see another thing. This case, if we consider, so here you understand what is this cross. It tells that magnetic field is perpendicular downward. If we consider this sheet of a page, then this cross will represent that field is perpendicular down. And if it is like point, if it is like this, then it means field is perpendicular upward. Now, this is magnetic needle placed in uniform magnetic field, and if it is little displaced, suppose through angle theta, then it will experience a force and it will start oscillating. So we can find the time period of oscillation also. Now, there is another point. A bar magnet is equivalent to solenoid. Definitely from this figure it is clear this is current due to, this is field lines due to a solenoid, this is bar magnet. Obviously they are similar. So we can say that all properties will be similar. Now here the same thing is explained. Let's read it together. This chapter is based on complete theory. So that is why I will tell you some basic facts, though you have to read yourself. The resemblance of magnetic field lines for a bar magnet and a solenoid says that a bar magnet may be thought of as a large number of circulating currents in analogy with a solenoid. Cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. The field lines remain continuous, emerging from one face of the solenoid and entering into the other face. One can test this analogy by moving a small compass needle in the neighborhood of the bar magnet and a current carrying finite solenoid, and noting that the deflections of the needle are similar in both the cases. To make this analogy more firm, we may calculate the axial field of a finite solenoid depicted in figure this. So here they are saying that if you calculate the magnetic field due to a bar magnet on its and suppose we take any point on its axis here, right, or we take a solenoid and we calculate magnetic field on its axis here. So in both the cases we will get this expression B equal to mu naught upon 4 pi 2m upon r cube, where m is dipole moment, magnetic moment. So what is that? Do you remember? If this is a magnet, this length is say 2L and pole strength is Qm each, right? So magnetic moment M is equal to Qm times 2L, right? So that thing we are talking about. So we can see that in the two cases we get same result. So that is why here the same thing is written, that to make this analogy more firm, we may calculate the axial field of a finite solenoid depicted in previous figure. We can demonstrate that at large distances, like this axial field resembles that of bar magnet. So both have same result. So result is like this, right? Here r is distance from the center of the magnet, so that we will calculate. Now next point here, some more. A bar magnet and a solenoid produces similar magnetic fields. The magnetic moment of bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. Now suppose dipole is placed in magnetic field, then what happens? Here dipole means we are putting a magnet in the magnetic field. In that case, we can calculate energy. There will be a torque, as we have seen in case of electricity, that suppose this is direction of uniform electric field, and if you put a electric dipole here, then one force QE will act in this direction, minus QE will act in this direction. Then we find torque equal to force into perpendicular. So QE into perpendicular distance, if this is 2L and this angle is theta, then 2L sine theta, right? I think you remember this thing. And then 2LQ we write as P dipole moment, then E sine theta, and then we write its vector form P cross E, etc. The same thing, the same analogy we can apply here. So if we find potential energy here, so we write this integration, this PE sine theta d theta. In same way here, torque, same as we have studied in case of electric fields. Here torque will be given by M cross B or MB sine theta. And now if we want to find out potential energy, then we rotate it through certain angle, and after that we calculate its potential energy, right? So we write here tau theta d theta, tau you know MB sine theta, and after putting mb sine theta, we integrate it. If you remember, integration of sine theta d theta gives minus cos theta plus c. If we put limits, in that case c will disappear. The same thing is happening here. So mb sine theta d theta, here we can write theta 1 theta 2, and then we imagine that theta 2 is 90 degree, theta 1 is theta. So after that we will get this result mb cos theta. And if we write in terms of dot products of two vectors, so m dot b, right? Here we can find the value of potential energy, stable equilibrium, unstable equilibrium, means on the basis of this theta. If we put theta equal to 0 degree, we will get minus md. If we put theta equal to 90 degree, then it will be 0. If we put theta equal to 180 degree, then u will be plus mb, because cos 180 is minus 1, right? So that will be case of unstable equilibrium. Stable equilibrium is theta equal to 0 degree, correct? So I think up to here you have understood fully. Now here there is a question: what happens if a bar magnet is cut into two pieces, transverse to the length and elongates the length? So two situations are possible. What will happen? Suppose you are given a magnet like this, and if you cut like this, then length will become half, but pole strength will remain same. If you cut like this, then what happens? Pole strength will become half. Suppose this is qm, then this time this will be qm by 2 for each, right? So we can calculate magnetic moment in both the cases. Right here length will be halved, whereas qm will remain same. Here qm will become qm by 2, whereas length will be same, right? So here we can see the answer. But let's read second question also. A magnetized needle in uniform magnetic field experiences torque, but no net force. So total force on the two poles will be equal and opposite. They will cancel out. That is why there is no net force. But torque will be, since there is a couple, so it is rotating it in magnetic field. Hence there will be a torque. So here so answer to first case. In either case, one gets two magnets, each with a north and south pole, that I told you. No force if the field is uniform. The iron nail experiences a non-uniform field due to the bar magnet. There is an induced magnetic moment in the nail, therefore it experiences both force and torque. The net force is attractive because the induced south pole in the nail is closer to the north pole of magnet than induced north pole. So question we have to read again once, because here question says a magnetized needle in a uniform magnetic field experiences a torque but no net force, right? An iron nail near a bar magnet, however, experiences a force of attraction in addition to torque also, right? So you have to see the difference between the two. So in case of here, first answer is no force if the field is uniform. In case of a magnet, we are talking about that. The iron nail experiences a non-uniform field due to the bar magnet, right? Keep in mind, for iron nail, there will be non-uniform field. There is induced magnetic moment in the nail, therefore it experiences both force and torque. The net force is attractive because the induced south pole in the nail is closer to the north pole of magnet than induced north pole, right? So this could be the cause. If you have not understood, so I can show you clearly. So suppose this is the north pole, this is south pole, and if there is a iron piece, so here south pole, this will be north pole, right? So definitely this is case of induced magnetism. So these two poles are closer, so there will be force of attraction than repulsion. Although north pole will repel each other also, but force of repulsion will be less than the force of attraction. So that thing they are explaining here. Now next point is, must every magnetic configuration have north pole and a south pole? What about the field due to a toroid? Generally, we know the basic concept that in case of magnet, there must be north and south pole, but here situation may differ. So answer to this question is not necessarily true only if source of the field has a net non-zero magnetic moment. This is not so for a toroid or even for a straight infinite conductor. So this you have to memorize. This is an important point. And then comes two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. We do not know which one. How would one ascertain whether or not both are magnetized? If one is magnetized, how does one ascertain which one? And you are given only these two. So one general test, if you remember, see, we can observe it. Suppose this is one piece, this is another piece, right? So suppose this is iron and this is magnet. If you bring this point closer to this, what will happen? It will be attracted. If you bring this point closer to this point, suppose magnet has north pole, south pole. So if you bring this point here, still there will be attraction. If you bring this point here, still will be attraction. It means definitely this is iron piece, right? But suppose it is, instead of iron piece, it is also magnetized. It means it has north and south pole. Then what happens? If you bring this point here, so there will be attraction. But if you bring this point here, then there will be repulsion. If such thing happens, that then you can say that this is magnet, this is magnet. Correct? So such a logic can be applied. Let's see the answer, what they are saying. Try to bring different ends of the bars closer. A repulsive force in some situation, it establishes that both are magnetized. If it is always attractive, then one of them is not magnetized. In a bar magnet, the intensity of the magnetic field is the strongest at the two ends, that is on their poles, and weakest at the central region. This fact may be used to determine whether A or B is the magnet. In this case, to see which of the two bars is a magnet, pick up one, say A, and lower one of its ends. First one on one of the ends of the other, and then on the middle of B. If you notice that in the middle of B, A experiences no force, then B is magnetized. If you do not notice any change from N to middle of B, then this thing I think you have not understood. So I am going to explain you. Suppose this is a magnet. So this is north pole, this is south pole. The basic concept is that magnetism at this end and at this end is maximum, but at midpoint there is very less magnetism. So if this is iron piece and you bring it here, it will be experiencing attractive force. If you bring it here, still there will be attractive force. But if you bring it here and you feel that there is no force between these two, it means definitely this will be a magnet. Reverse case, if you take, suppose this is iron piece and this is magnet, right? North south. If you bring this magnet here, it will be attracted. If you bring this magnet here, it will be again attracted. If you bring it here, still it will be attracted. So you can easily decide that at any point attraction is same, means strength of attractive force is same, so you can say this is iron. So this is one important aspect that you have understood. Now we are going to analyze another point, that is the electrostatic analog. So here a very simple thing, to find analog, what do we do? Like B will be replaced by E. 1 upon 4 pi epsilon naught will be replaced by mu naught upon 4 pi. Right? So such changes, like dipole moment in case of electric field is P, whereas in case of magnet it is M. And if you remember, electric field due to a dipole on its axial point, we have evaluated as 1 upon 4 pi epsilon naught 2p divided by r cube. Similarly, E equatorial we have found as p upon 4 pi epsilon naught r cube. So here, in case of E, we can write b. In case of p, we can write m, and r will remain same. In place of 1 upon 4 pi epsilon naught, we can write mu naught upon 4 pi. So we will get all results like, as we have seen the different points, how we are going to change. So let's see here, b equatorial will be mu naught m divided by 4 pi r cube. Likewise, the b axial will be this mu naught upon 4 pi 2m r cube. Here sign is just opposite, that is why minus sign is used. Here direction is just opposite, that is why minus sign is used. Now, next point. So the same thing is written here. What analogy we can use when we compare the electrostatics with magnetism? Dipole moment, we know we write P in case of electrostatics, and this is equal to, if you remember, Q times separation. Suppose separation is 2L, so Q into 2L. Here this is Qm into 2L, right? Similarly, equatorial field for short dipole is P upon 4 pi epsilon naught r cube. Here it will be mu naught upon 4 pi m divided by r cube. Axial field for short dipole is 2p divided by 4 pi epsilon naught r cube. Similarly, this becomes mu naught 2 pi mu naught times 2m upon 4 pi r cube. Then torque is P cross E here, m cross B. Then external field energy, potential energy, minus P dot E here, minus m dot B, right? So up to here, I think you have understood. We will study next thing in next lecture. Thank you for watching. Team Educate